In this video we talk about minima, maxima and extreme values of functions. And here I show three curves which are from an electrocardiogram, which measures the electrical potential during a heartbeat. And when clinicians look at these pictures, they particularly look for the minima and maxima of this function. So most pronounced in the healthy case here is, for example, the R peak, which is really the heartbeat, but slightly before is a little minimum, and slightly after is a maybe larger minimum, and then before this heartbeat is kind of a P peak, and then afterwards a little bit later is a T peak. And so a doctor would kind of look at this pattern and then decide if a heartbeat is healthy or not. So in the second case, for example, the P maximum is much bigger than it really should be, and the minimum here is kind of missing. All right, the S minimum is much lower than it should be. So this is an indication for atrial hypertrophy. Or here on the right, you see that the whole T wave looks very different than it should look in the healthy case, and so this is an indication for infarction. So to identify minima and maxima of a given function can be extremely useful for diagnosis of a heart disease. So let's do a mathematical definition of all this. So let A be a number in the domain D of f. We say that f of A is a global maximum or absolute maximum if f of A is bigger than any other f in the domain. It's a global minimum if f of A is smaller than every other f of x in the domain. It's a local maximum if it is bigger than f of x near A, and it is a local minimum if it's less than anything else near A. These definitions are very intuitive. For example, in this curve here we have a local minimum right here, a local maximum right here, and then this guy is an absolute minimum or a global minimum, but also a local minimum. Now all these values are also called extreme values. So let's look at this healthy heartbeat again. So what are the local and global and absolute, etc., maxima and minima? Well, most pronounced is the absolute maximum, so this is R. And then the absolute minimum we can also identify, which is here in S. And the others are the local maxima or minima. For example, P and T are both local maxima, whereas Q is a local minimum. Let us look at an example where we actually can compute stuff. So find the absolute maximum and the absolute minimum for the function f of x is x squared on the interval from -2 to 5. And here the graph is shown, and you can clearly see what's happening. So the absolute minimum is right here, which is at f of 0 is equal to 0. But for the maximum, now we don't have something like what we maybe normally would consider to be a maximum. So there's nothing like this. So what is the maximum? Well, easy, right? Still, the maximum is present because the maximum is right this value. The function doesn't curve downwards again, it just stops. So we're looking at the interval from -2 to 5. So we stop at 5, and then this seems to be the maximum value. So there's an interesting theorem which is called the extreme value theorem, and it says that if we look at a continuous function on a closed interval AB, so where the boundary points A and B are part of the interval, then on this interval it attains its absolute maximum and minimum values. Here I show three graphs. The first function here has an absolute maximum right here and an absolute minimum right there. The next function has an absolute maximum in the middle of the domain, and the absolute minimum arises on the boundary. Well, this can happen. So then this is the absolute minimum. And this function has several local maxima and minima. It has chosen explicitly so that this is all the same level. So we have 2 points where the absolute maximum arises. So this and this are locations for the absolute maximum. And then this here would be the absolute minimum. So it doesn't have to be unique. It can be several values who arise as maxima or as minima. Here are counterexamples where this does not work. So for example, the function on the left does not have a maximum. just because this point here is not part of the curve. It does not have an absolute maximum. Oh, this is strange. Well, but the reason is it is not continuous, right? We have a jump discontinuity sitting right here at 1. Of course, there are not continuous functions who do have maximum values, but it's still just not guaranteed in that case. Here on the right, we have that the function diverges near 2, it has a vertical asymptote, and so it is not continuous at this point, and it also does not have an absolute maximum. There's a very interesting connection of minima and maxima to tangent lines, so I really need to show you how this works. So here is again this animation which I have shown in earlier videos from Nelson Publishing, which is on their WebDesign websites. And so what you see here is the curve cosine x, and then there's a point in red and the tangent line in red as well. And with a slider down here I can move the tangent line around and it follows the curve very, very smoothly. We talked about tangent lines before. So where are the minima and maxima? So the minima are down here, the maximum is here, a minimum here, a maximum there. And let's see what the tangent line does at the maxima or minima. And now I have to move very slowly, it's very delicate. And you see what? The tangent line becomes flat. The tangent line becomes horizontal, as it seems. So let's try that for the minimum down here. So if I go there, then the tangent line, if I stop at the right moment, now come on, a bit more, a bit less, a bit more. I don't really get it. I'm slipping over the minimum. So let's try the other one. Okay, you see my point. So at the real minimum, the slope should be 0. It's a real minimum. Let's try a different function. So this one has a nice maximum right here, x times e to the minus x. And then I slide over the top, and indeed, at the top I have a horizontal tangent line. Here you see, the slope is 0.00. So that's cool. So we call this Fermat's theorem, because Fermat was somebody who observed this relationship. So if f has a local maximum or minimum at a point A, and if f prime exists, then f prime at this location is 0, and we knew f prime is the slope of the tangent line. And then we include a definition in this context, so we call something to be a critical number of a function f that is a number in the domain of f so that either f prime is 0 or f prime does not exist. The occurrence of the condition f prime at A does not exist in the definition of critical points is kind of curious, but here's a very good example which shows why this inclusion is important. For example, the function f is absolute value of x. Right, so here the function is shown, this is absolute value of x. It has a clear absolute minimum right here. However, the function has no derivative at this point 0. Right, we know that f prime at 0 does not exist for this function, but still it is a minimum. So this is one example which shows why it's important to include both conditions for critical points. Either f prime is 0 or f prime does not exist. And minima or maxima can arise at these kind of cusps of the function. What we have seen earlier about the closed intervals can be used to find absolute maxima and minima values. This is called the closed interval method, and it goes like follows. So to find an absolute maximum or minimum of a continuous function on a closed interval AB, we do the following. We first find f for all critical numbers inside this interval, and then we evaluate f at the boundary points, and then we find the maximum or minimum among those points. So this is really a super simple mechanism. Let's try it out in this example. So find the absolute minimum of maximum of x is x cubed minus 3x plus 12 on the interval minus 2 and 2. And so here I plot the function, and now it's hard to say with the minimum, right? This is a minimum maybe, and this is certainly a local minimum, but is it an absolute minimum? So hard to say. From the picture I can't say. Same for the max. So which guy is the absolute maximum? Okay, not clear. Let's figure that out by the closed interval method. So what was the method? Well, we first need the critical values inside the domain. So let's do that. Then we need to differentiate the function. F prime of x is 3x squared minus 3, which is also 3 times x squared minus 1. At critical values, this is equal to 0, so the critical values are plus and minus 1, which is right here, here, and here. And you see in the graph, this is indeed where we have a local maximum at -1, a local minimum at 1. We need to compute the value of f at those points. So f at -1, let's use the formula from above. So this is -1 plus 3 plus 12, which is 14. And f at 1 is, again, this formula 1 minus 3 plus 12, which is equal to 10. So in the next step, we should compute the values at the domain boundaries. So second, so here the domain was given at -2 and 2. So then f at -2, again, use the above formula. So this is -8 plus 6 plus 12. So this is 10. And then we have f of 2 is equal to 8 minus 6 plus 12, and this is 14. You know what? So the 14 and the 14 are the same numbers. So let's use maybe pink. Right, so this 14 equals this 14, and this 10 equals this 10. So it turns out that the minimum and the maximum do arise at all those points. So the absolute minimum is here and also here. So the absolute minimum arises at x is -2 and at x is equal to 1. And similar for the maximum, arises at x is -1 and at x is 2. Nice. Let me summarize. A continuous function can have various local maxima and minima. If f prime at a maximum or minimum exists, then f prime at a is equal to 0. So this if is actually wrong here. And we have seen the closed domain method, so that global maxima and minima of continuous functions can be found either at critical points or at the domain boundary. And in fact, this is exactly what the method says. So you should first check the critical points. Now, to remind you, critical points are either f prime at a is 0 or f prime at a does not exist. And then we check the domain boundary. Finally, we identify the maxima and minima from 1 and 2. It's me. No, it's me. No, it's me. 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 It's me. What exactly are you doing?